we conclude the chapter on time-independent perturbation theory by talking about the hyperfine splitting. We'll start by talking about the electron-proton interaction, the spin-spin coupling that arises from that, and then talk about the 21 centimeter line of hydrogen. So like the electron, the proton has a magnetic dipole. We call it mu sub p, which is g sub p times E, the electron charge, over 2 m sub p times the spin vector of the proton. If you recall, the electron had very similar, except you have a minus sign because of the negative charge. You have g sub e and m sub e, and then s sub e. Now, for the electron, g sub e was about 2. For the proton, g sub p is 5.59. The proton magnetic moment creates a magnetic field that the electron perceives, and that magnetic field looks like a dipole. We can write this dipole field as b sub p is equal to mu sub naught over 4 pi r cubed times the quantity 3 times mu sub p dot into r hat times r hat minus mu sub p, plus a second term, which is 2 mu sub 0 over 3 times mu sub p delta function, three-dimensional delta function of r. So the Hamiltonian of the electron in the proton's magnetic field is what's called the hyperfine interaction, and it's given by minus mu sub e dotted into b sub p. We can just write that down. So h prime for the hyperfine interaction is mu sub 0 g sub p e squared over 8 pi m sub p m sub e times the quantity 3 times s sub p dotted into r hat times s sub e dotted into r hat minus s sub p dotted into s e over r cubed. And then the second term coming from this term here is mu sub 0 g sub p e squared over 3 m sub p m sub e, and then you have s sub p dotted into s e times the delta function for 3 dimensions. If we use first order perturbation theory, this gives an expectation value which is as follows. The hyperfine perturbation energy is then mu sub 0 g sub p e squared over 8 pi m sub p m sub e times the expectation value. Remember, it's first order perturbation theory, so you just take the expectation value of the Hamiltonian of 3 times s sub p dot r hat times s sub e dot r hat minus s sub p dot s sub e over r cubed. And then you have the second term, which is mu sub 0 g sub p e squared over 3 m sub p m sub e, expectation value of s sub p dotted into s sub e, times, because of the delta function, the wave function at the origin modulus squared. So this is our energy correction. Now, when you have L equals 0, it turns out that this first state goes away. So that simplifies our calculation if we're just considering L equals 0. And we're left with this correction here, which includes the expectation value of s sub p dot s sub e, which is really just a coupling between the proton and the electron spin. Just like we had spin-orbit coupling, we now have coupling between these two spins. This term here also depends on the expectation value, the value of the wave function at the origin modulus squared. But we know what that is. At the origin, psi 100, which is the ground state, is 1 over pi a cubed. The hyperfine interaction correction there, then becomes mu sub 0 g sub p e squared over 3 pi m sub p m sub e a cubed, where this is the Bohr radius, times the expectation value of the spin-spin coupling Hamiltonian, which is s sub p dotted into s sub e. We know how to do this. We've done the spin-orbit coupling already, so this means that the good quantum number involves the total spin, which includes the spin of the proton and the spin of the electron. So the total spin is now a good operator of the perturbing Hamiltonian. S is equal to S sub E plus S sub P. We can use the usual trick that we used before to take S sub E dot S sub P. You can generate by squaring S and solving for S sub E dot S sub P. When you do that, you get S sub E dot S sub P is equal to 1/2 S squared minus S sub E squared minus S sub P squared. And that means that the expectation value for the operator S sub P dot S sub E is simply h bar squared over 2 times the quantity S times S plus 1, where this is the total spin, minus S sub E times S sub E plus 1, where this is the electron spin, minus S sub P times S sub P plus 1, which is the proton spin. Now, since the proton spin and the electron spin are both 1/2, this becomes very simple. This is 3/4 and this is 3/4. And so we get that S sub E times S sub E plus 1 and S sub E P plus S sub P plus 1 is equal to 3/4. But the total spin, because you're summing two 1/2 spins, can either be 0 or 1. The 0 is a singlet, and so S times S plus 1 is 0. And the triplet, total spin S equals 1, is equal to, gives you S times S plus 1 equals 2. So you have two splitting of this of the energies into two energies. One energy is for the triplet, which gives you a prefactor from here, which is 4g sub p h bar to the 4th, divided by 3 m sub p m sub e c squared a to the 4th. And you multiply it times 1/4. For the triplet state, it goes up by 1/4. And for the singlet state, it goes down by 3/4. So what this looks like is you have an initial degenerate state for psi 1, 0, 0. The singlet, where the two spins are in a singlet state, the proton and electron spin, gets a lowered energy of minus 3/4 times its coefficient. And the triplet state gets a raised energy of plus 1/4 times the same coefficient in the front. So delta E, the difference between the two, is just 1 times this coefficient. And that turns out to be 5.88 times 10 to the minus 6 electron volts. If you calculate the frequency that corresponds to the emission from this line, and we'll talk about emission when we do time-dependent perturbation theory, but the energy difference can be converted to a frequency by dividing by h, Planck's constant. And this gives you 1420 megahertz. If you now calculate the wavelength, that's 21 centimeters. So this is the famous 21 centimeter line for astronomy. So the 21 centimeter line lies in the radio spectrum, and it passes easily through interstellar dust in the Earth's atmosphere. And you can see here, this is an image in the 21 centimeter range. So this is imaging in 21 centimeters of 3 galaxies. Well, of the M81 galaxy, the NGC 3077, and the M82 galaxies. And you can see that since the emission is from neutral hydrogen, the neutral hydrogen gives you these emission lines showing you that there are hydrogen filaments that connect all these 3 galaxies. You can map the distribution of hydrogen in this galaxy. You can find out, using Doppler shifts of the 21 centimeter line, mapping the speeds and the relative velocities of the locations in the galaxy, so you can see what the relative velocities are of the galaxies, if the velocity is at least lying in the plane of observation. And you can use this same 21 centimeter line for the study of Big Bang cosmology. The 21 centimeter line gives you information about the early universe from recombination, that is, when you start getting protons and electrons, and then hydrogen, to reionization, where you ionize the hydrogen and you now no longer have neutral hydrogen that can emit the 21 centimeter line. So the 21 centimeter line is extremely important in astronomy, and it comes from this hyperfine interaction from the ground state of the hydrogen atom.